Okay, are you able to see my screen?
Yes, sir. Yes, sir.
Okay, thank you. So, we will try to cover a couple of things over here. One one important thing that I will try to cover up is um, the tensor product of the two Hilbert's tensor product of two vectors, and we'll start with the tensor product of two vectors. After that, we'll move on to different theorems like spectral decomposition theorem, spectral simultaneously diagonalizable theorem, and then we move on to singular value decomposition, polar decomposition theorem. Once we move on to that, after that we will be talking about the postulates of the quantum mechanics. So this is the plan. So postulates of the quantum mechanics. So we will talk about the postulates, and then we'll talk about the measurement problem. We will talk about the measurement problem, and we'll talk about the projective measurements, general measurement operators, and finally we will be talking about the finally we will be talking about the pure states and mixed states. So this is the plan. If we can continue, if we can go then I hope that we can go up to pure state and mixed states. And in so then once I am go introduce the concept of the density operators, once I introduce the concept of density operators, then I will reiterate the postulates in terms of the density operators. For example, the evolution postulate, the measurement postulate, everything I will reiterate in terms of the density operators. So this is how the plan. But within the things, I also will try to interact with you in the sense that I will be asking little small problems, giving small problems, so that you feel comfortable on working out those problems. So we have talked about two kind of products, inner product and outer product. So outer product is, as we have seen, is a kind of an operator when acts on a vector, gives you back the vector, a different vector. And similarly, however, inner product is a kind of a linear functional which takes two vectors into account and gives you a scalar on which the scalar from the field on which the vector space is defined. So in case it is a complex vector space and defined over the field of complex numbers. So in case the inner product of two vectors from the will give you the a complex quantity, a complex number, right? So and we came to know that the vectors in the original vector space is called as the K vectors, and the corresponding dual space is known as the dual vectors. Now, whenever the dual vector is operates on the original vector, it gives you a complex number. Now we will talk about a kind of an product which is neither the inner product nor a outer product. It's a tensor product. So if there are two Hilbert spaces V and W, and this is a complex linear vector space. Each V and W is a complex linear vector space, so inner product space with completeness condition. These are two Hilbert spaces V and W. Then V cross W is and so the dimension, dimension of V is M and dimension of W is M. So that means in the basis of V there are M vectors, and in basis of W there are N vectors, right? So then V cross W is an mn dimensional vector space, right? Is an mn dimensional vector space. The elements of V cross W are nothing but the linear combination of the tensor products V and W of the elements of V and W of W, right? In particular, if we think all these terms in terms of the basis, let us say that I and J are the orthonormal basis of V and W. Then I cross J is a basis of V cross W. So that is how V cross W tensor product is defined. We use these abbreviations VW, VW or VW for tensor product. So all these kinds of notations are very much. All these notations are very okay with the tensor product notations, right? So What are the conditions that it will satisfy? One of the important conditions that it will satisfy for any arbitrary scalar z and scalar z and element v of v and w of w, z of v cross w will be equal to z of v cross w, or you can say it as v cross zw. So if there is a scalar z and v of and there is a vector v from the vector space capital V and the vector and w from the w, then we can say like that. So this is so z the scalar multiplication over this v cross w is the scalar multiplication over the v and can be thought about as a scalar multiplication with the v vector, and similarly it can be thought about as a scalar multiplication with the w vector. Now if you take two vectors, if you take two vectors v1 and v2, then in v and w in w, then v1 plus v2 cross w is the v1 cross w and v2 cross w. So it is distributive across the tensor product is distributive. So we can see that it is distributive from w to v, and also similarly it is distributive from v to w. So v cross w1, it can be written as v cross w1 and plus v cross w2. So linear operators. Now how do I define? So this is the properties of the vector of the tensor product space v cross w. But how do I define linear operators acting on such a tensor product space, right? So let us say that there is a linear operator from let us say that there is a linear operator from a v to v and b w to w, and then a cross B is a linear operator from V cross W to V cross W. And how a cross action of A cross B is defined on any arbitrary vector in V cross W. So this is summation AI, Vi cross Wi is nothing but an arbitrary vector in V. In V cross W, where where Vi is a vector in V and Wi is a vector in W. They are the corresponding vectors. Now, if you take a linear combination of this Vi cross Wi, and get it acted upon by a tensor product A cross B, then how this tensor product A cross B will act? A will act on the vector space V, and B will act on the vector space W. So in principle, you can write it down as summation AI, A of Vi and B of Wi. So this is how. So then if you think A to B as a linear operator from V to another vector space V prime, and W to be a linear operator from W to W prime, any arbitrary linear operators C from V cross W to V prime cross W prime, the C V cross W to V prime can be written as a linear combination of these two operators. So C is a linear operator from V cross W to V prime cross W prime. Then, and if A is an operator from V to V prime and B is an operator from W to W prime, then the whole C can be expressed as a combination of these operators Ci AI cross Bi. So then how the action of Ci AI cross Bi acting upon V cross W? So this will be given by Ci, summation of Ci AI acting on V, and Bi is acting on W. So this is the action of the tensor product of the linear products in a tensor product of the linear operators. This is action of a general linear operator on elements of V cross W. Right now, so we have defined how the elements of the V cross W will look like. We have also defined what are the properties it will satisfy, and also we have defined them. We have seen that it is distributive. We have seen and also we have seen that how to define the linear operators on this tensor product space. But how will I define an inner product on how we are going to define an inner product on this tensor product space? So the inner products on the space V and W can be used as a natural inner product on V cross W. For example, if you take these two vectors, summation, this is a general vector of vector Vi cross Wi, linear combination of the vectors of Vi cross Wi, summation Ai Vi cross Wi. Another vector you take from V cross W, summation J, linear combination of these particular vectors, these tensor products Vj prime and Wj prime, and these are the complex coefficients Bj and Ai are the complex coefficients. It is like A1 V1 cross W1, A2 V2 cross W2, A3 V3 cross W3. Similarly here it is V1 prime cross W1 prime plus B2 V2 prime cross W2 prime. So when you take the inner product of these two general vectors, this will give you Ai star Bj, the inner product between Vi and Bj, because they are from the vector space V and a similar same vector space V, and similarly Wi and Wj, which is also from the vector space W. So the entire inner product on the inner product space, entire inner product of the two vectors of V cross W will be defined in this fashion. So how will I define the inner product? Tensor product of two different operators, right? So if A is an operator which is characterized by the matrix A11, A22, A1n, mm. So size of the matrix is m cross n. Any operator m cross n. Similarly, B is an operator which is characterized by the matrix P cross Q. Then the tensor product of these two matrices will be written in this form. So A11B, A12B, A1n B. So with each A11, the B will get multiplied. So the total number of elements in the row will be m times m into P, and the total number of elements in the column will be nq. So A is a m cross n matrix and B is a P cross Q matrix, right? So so in this way we can construct the get the matrix representation. In this way we can get the matrix representation of the product, the tensor product of the two tensor product of two operators, right? So not only the operators but tensor product of two vectors, we can also similarly do a matrix representation. So 1 4, for example, if you take this column vector 1 4 cross 2 3, right? So how will you multiply? So 1 2 so 1 gets multiplied with both 2 and 3, so you get 1 cross 2 1 cross 3. Similarly 4 gets multiplied with 2 and 3, so similarly you get 4 cross 2 and 4 cross 3. So this is the tensor product between the two vectors, right? So hope up to this it is clear. Is it clear?
Yes, sir. Yes, sir.
Thank you. Okay, so let us move on to the next problem. So we will talk about certain matrices which is called polymatrices, which is also known as the SU2 generator. So and we want to let us do some exercise over here. So so these are matrices. Why these matrices will be important? Because you will see these are nothing but the with the addition of the Planck constant by h by 2, they actually forms the spins of the system, spin operator of the system, sz, sx, xy, sy. But let us first of all see what are these matrices. So for example, if you take sigma 0 is this identity matrix, and sigma 1 is the x gate, or you can also with an addition of h cut by 2, it will be also be called as sigma x sx, right? Sx, and the spin of the particle in the x direction. So we while I was doing in the while I was doing this Sturm-Gallage apparatus, I was talking about spin sx and sy sz. So So this is the spin operator, Sx operator, right? So it has two eigen values, that is Sx plus and Sx minus, and of course there is an constant constant term multiplication over there, which is h cut by 2. But I will come to the spin separately, but there is a slightest difference. So this is called the sigma 1, this is your sigma 2, which is also corresponding to Sy. This is called the sigma 3, which is corresponding to Sz, and you can call it as a Z operator. So now I am asking you to check out all these conditions. Show all these matrices are unitary. I told what is an unitary. I told what is an Hermitian matrix. So all these matrices are Hermitian. Now also find out the operator representation of these matrices in terms of the outer products will be given in this way. For example, sigma 0. So this is in the basis 0 1 basis, computational basis. So the operator representation will be different in a different basis. So for in the computational basis, when your basis vectors are 0 and 1, so the operator representations of sigma 1 will be sigma 0 will be 0 0 1 1 plus 1 1, and sigma 1 will be 0 1 plus 1 0, and sigma 2 will be minus I 0 1 minus I 0 1 plus I 1 0, and sigma 3 will be 0 1 0 0 minus 1 1. So this is the operator representations, right? How to represent a matrix in terms of the in an operator representation is a very important thing. So for example, as I told you, the matrix elements, this is nothing but the coefficient of the element of the outer product 0 0, the coefficient of the element of the outer product operator 0 1. So this 0 is the coefficient of the element of the outer product 1 0, and this is the coefficient of the element of the outer product 1 1. So similarly, all these matrices sigma 0, sigma 1, sigma 2, sigma 3 will have an operator representations, right? Now these are the questions that I really want you to check it out. At least some of you can tell. So find out the eigenvalues of the poly operators. Now, and number 4, express all the poly operators in the plus minus basis, where plus is nothing but 1 by root 2 0 plus 1, and minus is nothing but 1 by root 2 0 minus 1. Can anybody tell me? Just so eigenvalues will be 1 and minus 1 for whom? But this is an exercise where you can check. Will give you confidence on operating different types of things in quantum mechanics, dealing with the. So you can check all these matrices are unitary, and also all these matrices are Hermitian. And also, I am asking you, which is this is the exercise that I want to see. And I'm asking you, write these operators. Write these operators in terms of plus minus basis, matrix representation, and also operator representation. Can you write down? So in terms of plus minus basis, it is out of these 4 operators, which 2 operators are diagonal in the 0 1 basis? Sigma 0 and sigma 3. But the other 2s are not diagonal in the 0 1 basis. So tell me which basis this sigma 1 and sigma 2 will be diagonal?
Sigma 3, sir.
Sorry?
Sigma 3.
Sigma 3 is a diagonal in this basis, right? And which basis sigma 1 and sigma 2 will be diagonal?
Sir, kindly share the screen, sir.
Sure. Just at least tell me the basis representation. Don't need to, I'm not bothering that you, I know that you will be able to show that unitary and the Hermitian and the, now my only, I was just want to see two things. One is that how you are representing these polymatrices in plus, say for example in plus minus basis, what is the matrix representation, and also so tell me which basis, which operators are diagonal.
I think, sir, sigma 2 and sigma 3 may be diagonal, sir.
But sigma, which in 0 1 basis, which are diagonal? Sigma 1 and sigma 2, you are saying?
Sigma 2 and sigma 3, sir.
But sigma 3 is already diagonal in the 0 1 basis, right?
Yes, yes, sir.
Then how can it be diagonal in a different basis? This is the eigen basis only. So it will be diagonal
Sir,
in its eigen basis. So eigenvalues of sigma 3 is
I am sorry, sir. I am checking on the basis of different eigenvalues. If any matrices have the different eigenvalues, then the that matrices will be diagonal.
So in the eigenbasis it will be diagonal. So basically
Yes,
you
sir.
have to find out the eigenvalues and the
I-
eigenvectors.
Exactly, sir. If 2 cross 2 matrices have the two different eigenvalues,
Yeah.
then it will be diagonal, sir.
So that is what I am trying to know is which basis sigma 3, sigma 2 and sigma 1 will be diagonal.
And sigma y
At
is
least from this. So let me clarify my question once again. You can easily see that sigma 0 and sigma 3 are already diagonal in the 0 1 basis. So I am so it is I know that for sigma 0 eigenvalue is 1 and 1, both are 1, both eigenvalues are 1. For sigma 3 it is very clear that both the eigenvalues are 1 and minus 1. However, in case of sigma and sigma 2, this is not diagonal because the off diagonal elements are there and also diagonal elements are 0. It must be diagonal in some other basis, which is the eigen basis, right? Which is the eigen
Yes,
basis. So I'm trying to figure out from you what is that basis where sigma 1 and sigma 2 will be diagonal.
So we need to find out the eigenvalues for sigma 1 and sigma 2.
Okay. I just give you 5-minute time. So just try to, if you can find out the eigenvalues and tell me the basis.
Okay, okay, sir. Okay. So I think sigma 2 is diagonal on a real space and sigma 1 is diagonal in real space and sigma 2 is diagonal in complex space.
Okay. So what is that space? At least tell me for sigma 1.
So for sigma 1 we find the eigenvalues are 1 and minus 1.
Sorry, you sigma 1 and minus 1, but what are the eigenvectors? I am just asking the basis. I know the eigenvalues will be 1 and minus 1. That is, you are right, absolutely right. But what are the eigenvectors?
Okay, sir. Just find out, sir.
So eigenvector is 1 1 and 1 minus 1.
Okay, 1
1 1 and 1 minus 1. And if we normalized it, it is 1 by root 2. There will be normalization coefficient.
So, okay.
And for sigma 2, it is 1 I 1 minus I. And if we normalize this, it again 1 by root 2 there will be.
So I am just okay, fair enough. So my point is, so if
But we can write it again in the that basis, 1 0 and 0 1 basis.
so 1 by root 2 is fine. Means I am saying that sigma x or say sigma 1 is diagonal in this plus minus basis. Plus is nothing but 1 by root 2 0 plus 1, and minus is nothing but 1 by root 2 0 minus 1.
Yeah, they are diagonal. They are okay, but they are not. Sigma 1 and sigma 2 is 1 1 and 1 minus 1, and so
Sigma 2 is spin. Okay. There's a lot of noise coming out. Okay, so somebody says sigma 1, sigma 2 will be diagonal plus. Yes, plus kate plus is the eigen. George Vicious has written is the eigenvector of sigma 1. Absolutely. Kate plus and kate minus will be the eigenvectors of sigma 1. Right. So here somebody has written down the comment, George Bishwas, and he is absolutely right. Plus kate plus and kate minus will be the eigenvectors of this sigma 1. Right. So in this basis, I told you to write down the operators in that basis, right? I told you to write down the operator in the plus minus basis. So in these plus minus basis, you will see a very interesting thing. So you will see sigma 1 will be diagonal. Sigma 1 will be diagonal in the plus minus basis, whereas sigma 3 will be off diagonal in the plus minus basis. So whenever there is a matrix representation, the basic point is to tell whenever there is a matrix representation, and there will be it is important with respect to which basis I am doing the matrix representation, so that there is a basis associated with the matrix representation. So you should not take any particular matrix representation as a universal, because matrix representation is a choice of basis that is I am making. So there are some important points. Other than after this, I think you will be able to do these problems. So some important thing to note over here, that normal matrix is Hermitian if it has a real eigenvalue, right? You can check. This is again a linear algebra proof. You can check that the normal matrix is Hermitian if it has real eigenvalue. Suppose A and A double prime are two matrix representations of the same operators A in two different bases, say Vi and Wj. Then what happens? So AI is the matrix representation. So AI and AJ is the matrix representation of the operator A in two different bases, Vi and Wj. Aij prime is equal to Aij prime is equal to Vi A Vj. So the ijth element of this matrix representation with respect to Vi is Aij prime, and it is given as Vi A Vj, right? Similarly, the matrix representation of A double prime Ij in the basis Wi and Wj, ijth element will be given as Wi A Wj, and characterize the relationship between. Now the question that I'm asking, that characterize relationship between this A prime and A double prime, right? how these two matrices are connected with the rest, which are defined with this help of these two eigenvectors, vector set of vectors vi and wj. So similarly, you can I have given you the sigma I and sigma j representation of sigma I and sigma j. You can find out the tensor product of these, all the possible tensor products of these poly operators. Also you can check what will be the value of sigma I cross sigma j, because you know how to do tensor multiplication between two matrices. So using that kind of technique, one can easily check out what will be the value of sigma I cross sigma j for all I and j. This is an I'm just asking you to find out one possible value, sigma 1 cross sigma 2. What is that value come out? Can you find out sigma 1 cross sigma 2? Can you find out sigma 1 cross sigma 2? What will be the tensor product of sigma 1 cross sigma 2? Hello. Hello.
Yes, sir. Yes, sir.
Sorry. My network connection is down. Sorry. Okay. Let me come back to the where I was last there. Okay. Next we will introduce the concept of commutator and the anti-commutator. So the commutator between two operators A and B is defined by this AB minus BA. So if A and B commutes with each other, we will have AB is equal to 0 and then AB is equal to BA. We say that A is commuting with B. Similarly, anti-commutator between two operators A and B will be defined by AB, with this AB as a curly bracket with this notation, where AB plus is equal to AB plus BA. Now we will say that A anti-commutes with B if AB is equal to this curly bracket AB goes to 0. Suppose A and B are two Hermitian operators, then AB is equal to 0 if this theorem tells you if there exists an orthonormal basis such that both an A and B are diagonal with respect to the same basis. Then in such a case, we will say that both A and B are simultaneously diagonalizable in this case. So let A and B are diagonal in the same orthonormal basis. So we'll prove we'll first prove that A and B are diagonal in the same orthonormal basis. Then we'll show that AB the commutator goes to 0. So that means we are assuming that A and B are diagonal with respect to the same basis. Then we'll show that AB will be equal to 0. So let us say that A and B are diagonal with respect to the some orthonormal basis I, and so since it is diagonal, so we can write down the A as lambda I I with this and B as lambda prime I, while lambda I and lambda prime are real, because we know that for a these A and B are Hermitian operators, so they will be diagonal in their eigenbasis. Okay, so you can write AB as AB minus BA. So you can write down this lambda I in so AB will be nothing but lambda I prime I. So this will be equal to 1, and similarly over here will be this quantity inner product between I and II will be 1. So it will be only the outer product II will be there. So we can separate out the outer product and we can have the coefficients lambda I lambda prime minus lambda I prime lambda I. So these two coefficients will be same because these are real eigenvalues. So in that case this will be 0. So this will be, so A and B will commute. So if they are have the same diagonal in the some orthonormal basis, they will commute. They will be the commutator will be 0. The interesting part will be the converse one. The converse states is let AG be with an orthonormal basis. So VA is the eigenspace of A with the eigenvalue A. VA is the eigenspace of A with the eigenvalue A, and J indicates J here indicates the degeneracies, right? So in this, let us go back to the previous slide where I was defining. Just a second. So I am So the basis, the orthonormal basis, I was characterizing by these vectors aj, right? So characterizing by this vector aj, where a is the eigenvalue of the eigenvalue, and j is the index to determine the degeneracies. Now, note that AB of AJ, since A and B, now here what we have to show, here it is given that AB is commuting with A is commuting with B. That means AB minus BA will be 0. That means AB is equal to BA. So here, so whenever AB is applied on this AJ, then we can always write it as BA AJ, because AB is equal to BA, and then AJ is an eigenvalue of the operator A. AJ is the eigenvalue. A is the eigenvalue of the operator A, and AJ is the eigenvector of the operator A. V and VA is the corresponding eigenspace made by the V suffix A is the eigenspace of A, eigenspace of A with respect to the eigenvalue small a, right? So in that case, VA forms an eigenspace which are made up of the vectors, eigenvectors, and they form a particular vector space which is called as the eigenspace with respect to the eigenvalue A. So whenever the operator A is acting on the eigenvector AJ, then it will give you the eigenvalue A with AJ. So it will come out to be AB AJ. As I have told you, BAJ is an element. Then what does it tell you? A when operated on B of AJ, A when operated on B of AJ, it gives you A B of AJ. So B of AJ itself is an element of the eigenspace VA, right? Because eigenspace VA are all those vectors in the eigenspace is made up of those vectors, eigenvectors, which when acted upon by A will give you a small a as an eigenvalue. So BAJ as a vector, when acted upon by A will give you is giving you the small a as an eigenvalue. So BAJ itself is an element of the eigenspace of A, right? So let us assume that PA is a projector to the eigenspace of VA, and then define BA as is the projector, BA as the operator when acted upon by PA on the B. So PA is something that is projecting an operator onto the eigenspace of VA. So BA is the projection of B on the eigenspace of VA, on the eigenspace of eigenspace VA. It is easy to check that the restriction of BA to the space VA is Hermitian. Since B is also Hermitian, PA is a projection operator. Projection operator will be there. Is also so so VA is an Hermitian. Is Hermitian and hence has a spectral decomposition. I will come to the spectral decomposition later. Any Hermitian operators by spectral decomposition theorem can be expressed in the diagonal form. So has a spectral decomposition in terms of orthogonal set of eigenvectors which spans the set VA. So let us call these eigenvectors ABK, where the indices A indicates A stands for the eigenvalue, B stands for the A stands for the eigenvalue of A, B stands for the eigenvalue of BA, and K stands for the extra index to allow the possible degeneracies in BA. Right. So so these are the eigenvectors of BA. So BABK is an element of VA. So what is happening? So sorry, just a second. So BABK is already an element of VA. So PAABK can always, since it's a projector, it can be written as PAABK is equal to ABK. So BAABK can always be written as, in place of ABK, we can put as PAABK. And from in place of BABK, we can always put as PABABK. So when BA acted upon this operator, BA acted upon an ABK, so B, it gives you the eigen value B. So because I have already told you that the B is the level of the eigenvalue of BA. So BA, when acted upon on these eigenvectors, this operator BA is when acted upon these eigenvectors, because I know BA is nothing but PA from here. BA is nothing but the projection of the operator B onto the eigenspace of VA. So what I am saying is that B of ABK, which can be further written down as PAABK, PABABK, and ABK can be written down as PAABK. So there are two PAs over here. So this together forms a BA, and here BA, when acted upon ABK, it will give you B of ABK. So it follows that ABK is an eigenvector of B with eigenvalue of B. So thus, what does it tell you? ABK itself is an eigenvector of both the operator A as well as the operator B. Thus, A and B are simultaneously diagonalizable in the basis, which is characterized by this ABK. Three indices. One is the indices that is coming from A. One is the indices that is coming from B. BA's projection of B on A. Another indices that is to count into the degeneracies, right? Okay. So once again, what is the proof? The proof is simple. You start with a projector onto the space projected PA, which projects into the eigenspace of VA, and we define this BA as the projection of the operator B on the eigenspace of VA. Now, so this operator BA is once again this operator BA has once again is Hermitian and has a spectral decomposition in terms of orthogonal set of eigenvectors, which will span the set VA. So B of ABK is an element of B of LA. So we call this eigenvectors, this orthogonal set of eigenvectors, as the ABK, where the indices A and B are to level the eigenvalues of A, and small b to level the eigenvalues of BA, and K is the index to denote the degeneracies. So B of ABK is an element of VA. So thus B of ABK, it forms an element of the eigenspace of VA. But we can also write that B of ABK as P of A ABK, because the projection onto this element will give you the same element, since this is an element on the VA itself. Now again, a P of ABK is nothing but ABK. So in place of ABK, we can easily put down in place of P of A ABK. So now you combine these two, the left hand side, combining this term before the K, that is PA, which is nothing but BA. So BA is an operator acting on the ABK to give you the eigenvalues B, because this is an eigenvector in the eigenvector corresponding to the operator BA. So whose eigenvalue is B? So thus we see that so ABK B is also an eigenvalue of not only of BA but also of B, and we see that ABK is also an eigenvector of the operator B. So ABK we have started ABK as an eigenvector of the observable A, but it turns out to be eigenvector of also the observable B, because of the commutative property. So that the ABK is an orthonormal set of, so both A and B are simultaneously diagonalizable. Is this clear? Then we'll move on to the spectral decomposition theorem.
Yes, sir. Clear, sir.
Thank you. So what does the spectral decomposition theorem tells you? The spectral decomposition theorem tells you that any normal operator M on a vector space V is diagonal with respect to some orthonormal basis in V. Now if you take any vector space in V, and you know, and we have a normal operator. So if you recall what is a normal operator, a operator will be called normal if a dagger will be equal to a dagger A, right? So it is telling you that any normal operator M on a vector space V is diagonal with respect to some orthonormal basis in V. Now if you remember, uh, the normal operator definition, it tells you that M will be normal operator if M dagger is equal to M dagger is equal to M dagger M, right? So, but and what is the converse of this theorem? The converse of the theorem tells you that any diagonalizable operator is also normal. So not only a normal we will find a basis where it will be diagonal with some orthonormal basis, normal operator, but also any diagonalizable operator is normal. So let us do the converse first. Let A be any diagonalizable operator. So and it is diagonal in its eigenbasis. So A is equal to lambda I. Lambda is the eigenvalues and I is the eigenvectors. So A dagger will be this one, lambda I star, and I'm not I didn't so why it will be lambda I star? We have not told that this is a Hermitian or something. It is just a diagonalizable operator. So it can be in general be complex numbers. So lambda I star will be there. So lambda I star II. A dagger will be lambda I star II. So A dagger will be mod of lambda I square II. So II, this will become 1 and this will also become 1. Similarly, A dagger A will be lambda is mod of lambda I square II. So both A dagger and A dagger A are equal. So then A dagger is equal to A dagger A. That means A is a normal operator. Okay, now the actual this is the converse. So if it is a diagonalizable operator, then it will be then this shows that that operator is also a normal. Now we have to show that given a normal operator, it will be always diagonalizable in some basis. So here I will ask you some important questions, and I want you to find out the answer of these questions. For example, let lambda. I will come to the question later. First, we start with this. Lambda be the eigenvalue of M. Suppose M is a normal operator. Lambda be the eigenvalue of this normal operator M, and P is the projector onto the lambda eigenspace. So when P applied on M, it will project it into the lambda eigenspace, right? And Q is the projector onto the orthogonal complement. So P plus Q is equal to P plus Q is equal to identity vector. So Q is the projector which will project into the orthogonal complement, right? So whenever the M can always be written in this form. Any normal operator, any operator M can be written in this form P plus Q. So you can break this into PMP plus QMP plus PMQ plus QMQ. So PMP is equal to lambda P, because P is the projector into the eigenspace, right? So P is is the eigenspace of this. So whenever m applied on p, it will give you lambda p, right? So lambda p square will be again p, since it is idempotent, p square is equal to p, you can always write lambda p square as lambda p. So pmp will be lambda p. However, qmp will be 0 because m will project p into the m will into p. So p and q are orthogonal to each other. So p and q are orthogonal to each other. So pq will be equal to 0 as m takes subspace m into itself. So we claim that, however, so out of these four terms, PMP is equal to lambda P, QMP is equal to 0. Now we are left with these two terms, PMQ and QMQ. PMQ, I am claiming that PMQ is 0. Why I am claiming so PMQ is 0? Let us see. Let V, so V be an element on the subspace P, right? Then dagger V is equal to dagger MV, because M is a normal operator. Since M is a normal operator, so lambda dagger V. So what does it tell you again? So dagger V itself is an eigenvector, because when M applied on dagger V gives you the eigenvalue lambda and keeps the dagger V. So dagger V is an the dagger V has an eigenvalue lambda, and therefore this eigenvector has an eigenvalue lambda, and therefore is an element of the subspace P. P is the subspace, P is the projector which is projecting into the eigenspace, which is the this is the subspace P. So dagger V is nothing but an element of the subspace P. So Q when applied on any element of the subspace P, this kind of projector, it will be always orthogonal complement. So it will always give you 0 from the orthogonality condition. Now, if you take the adjoint of this QM dagger P, you will get that PMQ. So right. So that is why I am saying that PMQ also 0. Now then, the normal operator can be simply broken up into two parts, PMP plus QMQ. Now we have to show that QMQ is normal. So PMP is normal, that is for sure. So what you can write QM as, you can write QM as QM into P plus Q. And we know that QMP is equal to 0, so QM will be equal to QMQ. Similarly, QM dagger will be QM dagger P plus Q. And you know that QM dagger P is 0 from the previous, that is PMQ is 0, so QM dagger P is also 0. So that is why QM dagger, it will be QM dagger will be QM dagger Q. So now you see that if you take QM dagger Q and QM dagger QMQ and QM dagger Q, Q square you can say Q. So in the next step, you can replace Q into Q by Q, Q square by Q. So QMQ, M dagger Q. Now M dagger Q, QMQ can be written as QM. QM can be written as QMQ. So for here I am replacing QMQ by QM and M dagger Q. So since M is normal, you can bring M dagger on this side and you can say that QM dagger MQ. Now QM dagger is nothing but QM dagger Q. So QM dagger Q, QM dagger Q. Because this Q will be now replaced by Q square. So QM dagger is replaced by QM dagger Q, and then QM dagger Q is replaced. Then that Q in the middle is replaced by Q square. So you can write QM dagger Q, QMQ, right? So which shows that QMQ and its conjugate is this one. So A dagger. So if QMQ is an A matrix and this is A dagger, so A dagger is equal to A dagger A. So which tells you that QMQ is a normal matrix. So by induction, now I want this answer. So by induction is also, by induction I am saying that QMQ is diagonal with the same orthonormal basis for P. Why I am saying this? Try to find out. Now, since they are diagonal with respect to the same ortho, both of them are diagonal with respect to the. See, if QMQ is normal, QMQ is also normal, and it is also QMQ is normal, and we have seen PMP is normal. So and QMQ is diagonal with respect to the same orthonormal basis for P. We can together say that M is also diagonal. But why by induction we can say that QMQ is diagonal with respect to the same orthonormal basis for P? Can anybody tell? Can anybody tell? Is this clear or not? Am I audible?
Yes, sir, you are audible.
Thank you. So
Sir, but nothing is seen in the screen. Only you are presenting to everyone is written there. Yes, sir, it is visible. Sir, you are not audible.
Oh, sorry. My microphone was on mute. Sorry. Okay. Let us come to the polar decomposition then. So polar decomposition, suppose A is a linear operator which is defined on a vector space V. Then there exist two operators, there exists only one unitary operator U and two positive operators J and K, such that A can be written as Uj and K also it can be written as Ku, where these unique positive operators J and K are given by J given by is root over A dagger A and K is given by root over A dagger. And where A is equal to Uj is called wave polar decomposition, where A is equal to A is equal to Ku is called the right polar decomposition, right? So we have to show that if there exists an unique positive operators J and K such that this will hold A is equal to Uj and K is equal to U. So these two operators are equivalent, means that it will whenever acted on the same set of vectors, these two operators will give you the, for all vectors I, kth vector I, this A and Uj will give you the same answer, right? So let us start with J as a root over A dagger A. Since it is a positive operator, and a positive operator is a Hermitian operator, and a Hermitian operator is a normal operator, so it can be given a spectral decomposition. So since it is a normal operator and it can be given a spectral decomposition, so we can always write J in form of some eigenvalues lambda I and eigenbasis II in the outer product notation. So here lambda I is greater than 0. Now we define a vector psi I, which is A applied on the eigenvectors I. Now, if you see, if you take the inner product of psi I and psi I, what it will come out? It will come out I, A dagger, A, I. So A dagger A is nothing but J. How I have defined J? Root over A dagger A. So A dagger A is nothing but J square I. So J square is what? Since J square is what? Lambda I square II, because it is a diagonal matrix, only the diagonal elements will be squared. So it lambda I square II. So you will get II, this will be equal to 1, this is equal to 1. So that means psi I is a lambda I square. So that means psi I is not a normalized vector. So we need to normalize psi, because when you take with psi I, if it is a normalized vector, then it will give you 1 as an inner product. But instead of giving you 1, it is giving you lambda I. That means to normalize psi, we introduce another vector which is called EI, which is psi I by lambda. Now, since EI is normalized, we can also check that EI is not only normalized, but it is orthogonal set of vectors. Because if you take a EI and EJ and you take the inner product between this EI and EJ, this will come out to be 0. So if I not equal to Z, then EI inner product EJ is equal to I A dagger A J. Because how I have defined EI? A times of I, A applied on I. So EI EJ will be I A dagger A J. Now I J square J lambda I lambda J. Now if you write down break down J square is nothing but lambda I square II. So whenever I takes the inner product with J, it will be 0. So as a result, the whole expression will come out to be 0. So we have been considering those I such that lambda I is not equal to 0. Now we can use the Gram-Schmidt process to extend this orthonormal set of vectors so that it forms an orthonormal basis, which we label as EI. Now then, in the next step, what we do, we define an unitary operator, which is U, EI, I. Now when U and J is together applied on I, what you will get? EI applied on lambda I summation of, because J can be represented as lambda I outer product of II, right? So lambda I outer product of II applied on I. So this will be 1, right? And lambda I will come out. So this and this will this II will take you to 1. So you are only left with lambda I EI, right? Whenever I is not equal to j, those will go to 0. So you will have lambda I EI. So lambda I EI is what? Nothing but psi I, and psi I is what? A of I. So for any I, uj and uji is equal to ai for all I. Now in this case, that means these two operators are saying a is equal to uj. So this is also true for lambda I whenever lambda I is equal to 0. So we argue that the action of a and uj agree on the basis I, orthonormal basis I, and thus a will be equal to uj. J is unique since multiplying a uj on the left by a dagger, what you will get? J u dagger, you will get j square is equal to a dagger a. So from which we can see that j again comes back to a dagger a uniquely, right? So a is equal to uj. This expression is unique because if you take the adjoint of the if you take the dagger of a and you will take uj dagger, it will become j u dagger, because for positive operator j dagger j will be equal because it is Hermitian operator. So in that case j will come out, and j of j dagger j will be equal to j. So j u dagger. So you can see that if you do a dagger a, you will still get back j square. So yeah, you will still get, because u dagger u will be I, from which we can say that j will be a root over a dagger a uniquely. So how about the right polar decomposition? The right polar decomposition, a is equal to uj, right? Now if I multiply uj by this I is nothing but u dagger u, so it will become uj u dagger u. So call this matrix uj u dagger as k, and this matrix as u. So what k is equal to uj u dagger is a, since j is a positive operator and u is a unitary matrix, it will not change its eigenvalues. So uj u dagger is also still, it remains a positive operator. So eigenvalues will be remain positive. So now you see that a dagger is nothing but a n dagger is nothing but ku u dagger k. So k square. So finally k square. So we have k is equal to a dagger a. So right polar decomposition a can always be written in the form k of u, where k is nothing but root over a dagger a, right? We know already from a is equal to uj from the use and create this operator k, and we see that k is a positive operator, and also we say that if we do we can get k to be as root over a dagger a. So then the matrix a not only can be written in the form the left polar decomposition uj, but also it can be written in the right polar decomposition form ku, where in case of the left polar decomposition j will be root over a dagger a, and this will be root over a dagger. K will be root over a dagger. So from the polar decomposition theorem, the next important thing that follows is the singular value theorem. What does the singular value theorem tells you? The singular value theorem tells you A be a square matrix, then there exist two unitary matrices U and V and a diagonal matrix D with non-negative entries, such that square matrix can always be expressed in the form U D V, where D is the diagonal entries of the D and are called as the singular values of the matrix A. So now it is very easy to follow from the polar decomposition that A can be any matrix A, square matrix A can be written as a product of an unitary matrix S and a positive matrix J from the left polar decomposition. Now by the spectral theorem, the positive matrix will have will follow the spectral theorem because it is a normal matrix, Hermitian and hence normal. So we can say that J is a TD dagger for some unitary T and the diagonal matrix D with non-negative entries, means this unitary will not change the these unitaries will not change the eigenvalues of the diagonal matrix, right? So and then if that is the case, we can easily set so if you write down J, if you plug in J as TDT dagger over here, it becomes STD dagger. So then you can say U to be as ST, U to be as ST, and V to be as T dagger. Then you can usually write down the matrix A as UDV. So you can replace J by T dagger, and you can say ST as U and ST as U and T dagger as V. Then it becomes UDV, right? Then A becomes as an UDV. Is it clear?
Yes, sir.
Yes. So, okay. Next, we summarize and move on to the postulates of quantum mechanics, right? So the very first important postulate is that associated to any physical system or a quantum system, that is a complex vector space which you have seen, and this complex vector space are supported within inner product uh, supported within inner product and completeness condition, and it is known as the Hilbert space of the system. This system is completely described by its state vector, which is the unit vector in the system state space, and is represented by the vector psi. And H is your state space, which is a complex linear inner product space, and along with the completeness condition, they together forms an Hilbert space. They together forms an Hilbert space. Right. So in reality, what is this psi? This psi can be either the spin of the silver atom or the polarization of the photon. Simple quantum system is an example. One of the example of a simple quantum system is a two-level system, which we otherwise known as the qubits. Right. For example, psi is equal to A0 plus B1, where mod of A square plus mod of B square is equal to 1. So where 0, 1 is the basis of the Hilbert space. So it's a two-level quantum system with 0, 1 as the basis. And mod of A square is the probability of getting 0 from the psi. But I will come to the probability, as I have told you, I will only come to the probability when I go to the concept of the measurement operator. So, but for the time being, you can say that mod of A square is the probability of getting psi into the state vector 0. The second postulate tells you the evolution of the quantum systems, right? Which gives you the evolution of a quantum system. So the evolution of a closed quantum system is described by the unitary transformation. For example, if you have a state of the system at a time t1 is psi and a time t2 is psi prime, then psi prime will be connected to psi with the through the unitary operator u, which depends only on time t1 and t2. Depends only on time t1
Sorry,
and t2.
sorry, sir.
Yes.
Sir, could you please hide this pop-up on the screen?
Could I hide?
hide this pop-up on the screen in the below?
Okay, thank you.
Thank you. Thank you.
So, as I was telling you, the evolution of a closed quantum system is described by the unitary transformation. The state of the system right now at this moment is at time t1 is psi, and at time t2 is psi prime. The psi prime is connected to psi with the help of this unitary operator u, right? And these dynamical equation of this will be given by the Schrodinger equation, right? So I have not written down the Schrodinger equation right at this moment. So there are two pictures associated with quantum mechanics. One picture is the evolution picture, which tells you how the states goes from one particular state to another particular state. Another picture is a collapse picture, which is the measurement, which gives you the measurement. So for example, psi is undergoing the evolution with the unitary operator u, and it is getting to psi prime, right? And because it is a two-level system, any vector a is 0 plus b1. So now if you try to measure, you will get with an say alpha 0 plus beta 1, you will get a 0 with a probability mod alpha square, and you will get 1 with a probability mod beta square, right? So can you probability with mod beta square. So as you can see in this small example, so 0 is going to 1. Suppose this is the basis vectors 0 and 1. Now what is this unitary operator which will take you 0 to 1 and 1 to 0? And what is the unitary operator which will take you 0 to 0 and 1 to 1? You can easily check. This is the Pauli spin operators which will take you, the sigma x will take you 0 to 1, 0 to 1 and 1 to 0, where sigma j, it is the operator which will take you 0 to 0 and 1 to -1. So as I told you before, these Pauli operators can also be treated as an unitary operators, or it also can be treated as a measurement or Hermitian operator, which I will come later, right? So sigma x is flipping the state of the system. So if you say, if it is in 0, it will take you to 1. You can check, apply sigma x on 0 and 1 and respectively, and you can check what will happen. Similarly, let me know what happen if you apply sigma y. What will happen if you apply sigma y? Can anybody tell what will happen if sigma y is applied on 0 and 1? Any guess? What will happen if sigma is applied to 0 and 1? Can you find out? Am I audible?
Yes, sir.
So can you find out then what will happen if sigma y is applied onto 0 and 1 vectors? The unitary sigma y applied onto 0, 1 vectors. Here in this example, I have shown you that when sigma x is applied on 0, it will give you 1, and 1 when applied on 1, it will give you 0. Similarly, when sigma z is applied on z as applied on 0, it will give you 0, and 1, it will give you -1. The unitary Hadamard gate h1 by root 2 1 minus 1 will take 0 to 0, 1 by root 2 0 plus 1, and 1 to 1 by root 2 0 minus 1. Now I have already asked you to verify sigma y, sigma x, sigma z are unitary. But for the time being, tell me if sigma y is applied on 0 and 1, what output I am getting from 0, which vector I am getting. Can you work out quickly sigma y applied on 0 and 1, what it is going to come? It is very simple. Okay. Anyway, let us go back to it once again. So the time evolution of the state of a closed system is described by the Schrodinger equation, and the Schrodinger equation is given by I h cut d psi dt is equal to h psi, where h is the h cut is the Planck's constant and h is the Hamiltonian of the system. So the third important postulate quantum measurements are described by the collection of measurement operators. These operators act on the state space of the system being measured. So the measurement operators are indexed by the measurement outcomes m. So if m indicates, the small m indicates the measurement outcome, right? So we are applying this measurement operator m on the on the state side to know what is the system, so why do we carry out a measurement? To know about the system. So to find out the what is there. But whenever we measure in the system, we collapses the into one of its eigenstates, right? It collapses into its one of its eigenstates with certain eigenvalues. So in general, I will come to the projective measurements or all these things later. But in general, measurement, if this measurement process is characterized by this set of operators m, so where m is the measurement outcomes, then it has the probability to the state of the system, and the state of the system after the measurement will be in the form psi m, and the probability that the measurement outcome m will be there, it can also be found out, right? So the probability of getting the measurement outcome is given by this psi m dagger m psi, right? So m when applied on psi will give you another state psi m. Similarly, the dual of that state will be given by psi of dagger, which is psi prime dual, and psi m. If psi m is the state or the psi prime is the state after the measurement, this will be given by this. So whenever psi, when applied on this operator, this measurement operator m is applied on psi, it will give you psi. Similarly, on the dual vector space, it will give you psi of dagger. So now if you take the inner product and square of this term, this will give you the actually the probability of getting the measurement outcome m, and which is written by psi dagger m psi. So the state of the system after measurement will be given by psi divided by root over psi of dagger psi m, because this is the probability amplitude, right? So root over this to normalize this kind of thing, to normalize the state, right? And you can easily check out that if m is the index of the outcomes, the total probability will be equal to 1. Summation of all this probability of getting the measurement outcomes m will be total probability equal to 1. How will you find out? For example, it's very simple to find out. So suppose you take summation of pm. So where summation of m psi dagger m psi. So pm can be written as summation of m psi dagger m psi. Now if you take the summation sign inside, and so this is what psi dagger m, this will be nothing but the sum, all the measure for the completeness condition, all these measurement operators will be identity. So this will be psi I psi. So psi is equal to 1. So the total probability will come out to be 1, right? So take a very simple example. You have a state psi a0 plus b1, and you have two operators m0 with the measurement outcome 0. The operator corresponding to is 0 0, and for the measurement outcome 1, the operator corresponding is 1 1. So m0 dagger is 0 0 again, m1 dagger is 1 1 again. Now if you find out p0, what is p0? P0 is psi m0 dagger m0 psi. So that means you can write m0 dagger as 0 0, and you can write m0 as 0 0. So psi 0 0 0 0 psi. So the 0 0 is 1. Psi 0 and 0 psi can be written as modulus of psi 0 square, which is nothing but the probability of mod of a square, right? The inner product between the psi and 0 is nothing but a, because psi is a0 plus b1. So if you take 0 0, which it will go to 1, it will remain a, and 0 1 will be go to 0. So this will be mod of a square. Similarly, you can find out p1 to be mod of b square. So m0 psi by a is nothing but this state, and m1 psi by a is nothing but this state. So this is a classic example how the measurement operators are acting on the state. Is this clear?
Yes, sir.
So Anindra, shall I stop here or continue in the next class? Okay. 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 Right. Right. Yeah. If you have any question, please ask. Thank you, Anindra. Thank you, Anindra. Thank you, Anindra. Thank you. So Friday we'll meet again at the Friday 11. Thanks. Thanks for being patient and listening to me.
Thank you, sir.
Thank you. Thank you.